Hello, calculus students. Today we have a lesson on exponential growth and decay. If that sounds familiar to you, that's quite all right. You have learned about exponential growth and decay before, and a lot of what we do today is actually going to be very similar to what you have done in the past. Let's say that we have some quantity of stuff called S, and as time passes, the amount of stuff changes. The rate that the amount of stuff changes as time passes can be written as a derivative, ds dt. There are many situations where the rate that stuff grows depends on how much stuff we have at the moment. Maybe sometimes we want to measure time in nanoseconds, and sometimes we want to measure time in hours. The way to compensate for that is with a constant. Math people like to use k for this constant. So ds dt, which is the amount of stuff that changes as time passes, is equal to k, which is some constant, times s. Oh, the above equation says the rate that the amount of stuff changes as time passes is equal to the amount of stuff we have times some constant. The constant could have been placed anywhere in the equation, but things work out best by putting it there. Problems usually go something like this. The rate that some particular stuff grows is proportional to how much stuff there is at that time. We start with 10 pounds of stuff, S. 4 hours later, we have 15 pounds of stuff. When will we have 20 pounds of stuff? We have been asked to find the value of time, t. Our equation does not have a t in it, but it does have the derivative of t dt. We have to find the integral of our equation to solve for t. Remember that the integral of 1 over x dx is equal to the natural log of x plus c, which could also be written as the integral of dx over x, see if we just multiply the dx on the top here, equals the natural log of x plus c. We can do some algebra to get ds over s by itself on one side of the equation, which is called separating the variables. So ds dt equals ks. So then we're multiplying by 1 over s on both sides. So ds over s times dt is equal to k. And then if we multiply by dt on both sides, we have ds over s is equal to k times dt. Now, if you integrate both sides, the integral of ds over s, which is kind of like this, the integral of dx over x is equal to the natural log of s, and the integral of k dt is k times t plus c, because you've got to remember that k is a constant, some regular old number. We would like to have s by itself since it is the dependent variable. So if you exponentiate both sides by saying e to the power of the natural log of s is equal to e to the power of kt plus c, that makes the e and the natural log kind of undo each other there as inverse operations, leaving us with s equals e to the power of kt times e to the c. That's because when you have the same base, you add the powers. So here we've split it into two by using the same base on each part of this sum. And e to the c is some constant, e to some constant, which is going to give you some other constant. So s is equal to that constant times e to the power of kt. And you can say y, the amount of stuff after a certain amount of time, is equal to c, the initial value, times e to the power of k, which is your rate, times t, which is your time. This is closely related to the formula that you learned in Algebra 2. A equals P e to the RT. That was called the PERT formula, which was used for finding the amount of money after some amount of time with continuous compounding, P being the principal that you start with, and R being the rate, which is what our K is here, that the money is either growing by or decreasing by the percentage rate of the investment, usually written as a percent. So this equation and this equation are just basically using the same concept with different variables, okay? So let's do some example problems together. And by the way, you will need a calculator for today. So I'm going to write this formula at the top of the page. Y equals C e to the k t power. Number 1 says E. coli bacteria double in population every 30 minutes. If the initial population is 85, what is the population of bacteria after 3 hours and after 1 day? So let's look at what the ending amount is. It doubles. So whatever, when you say doubling, the ending amount could be like 2 and the beginning amount could be 1. It really doesn't matter. That's just the ratio of their relationship. Times E raised to the power of K, which we do not know, times T, this is every 30 minutes. And then our units switch to hours and days. So I'm going to go with hours and say 30 minutes is 0.5 of an hour. Yeah, I'm going to use hours for my units in time. 0.5 hours is 30 minutes. So now I'm going to try to solve for K here so that I can write an equation that relates the amount that's left with the time that's passing. So I'm going to exponentiate both sides. Actually, no, I'm going to take the natural log of both sides to get the k out of the power. Natural log of 2 equals the natural log of e to the 0.5k. So that undoes each other, and we have natural log of 2 equals 0.5k. And then I can divide by 0.5, or that's the same thing as multiplying by half here. So I could multiply times 2 on both sides and get 2 natural log of 2 is equal to k. So I've got my time measured in hours in this equation, this relationship. So the y is going to equal the starting population, 85, times e to the power of k, which is 2 natural log of 2, times, we want to know after 3 hours, so times 3. And then we'll just use the calculator to compute that value. 85 times e to the power of 2 natural log of 2 times 3. So that gives me an ending amount of 5,440. There we go. That's after 3 hours. Now after 1 day, since my time's in hours, I'm going to have to use 24 hours for my 1 day time. 85e to the 2 natural log of 2 times 24 hours. So I'm going to press second enter to pull up what I just had and change my 3 to a 24. Ooh, this is a big number. I'm going to leave it in scientific notation. Y equals 2.393 times 10 to the 16th power. This e on your calculator means 10 times 10 to the power of whatever number follows it, the 16. And we still want to give 3 decimal places after our decimal, even though we're working in scientific notation. Okay, so that's the end of example 1. Let's take a look at example 2. It says you decide to borrow money at 22% interest per year. How much will you owe on a loan of $5,000 after 1 year and after 3 years? Okay, so the amount of money that you owe will be the ending amount, which is the y equals. The beginning amount that you borrowed would be 5,000 times E. The interest rate is 0.22. 22% is a decimal as 0.22. And then we have our time. And the question has 2 times, 1 year and 3 years. So we'll plug in 1 for time. And we'll do another one where we will plug in 3 for the time. And that'll give us our 2 answers. So, clear this out. 5,000 times e to the power of 0.22. So the 1 year will be $6,230.38. This is a money problem. We're going to leave our dollar amount in dollars and cents. And now I'm going to press second enter to pull it back up, and I'm going to take my 0.22 and multiply it times 3. We didn't really have to put times 1 on the other one because obviously anything times 1 is itself. So here we've got y equals 9,673.96. All right, number 3 says the population of Bloom Falls, Massachusetts, population 937, is slowly moving to a bigger city. Every year the population drops by 4.5%. What is the population after 3 years? All right, so the beginning amount is 937. And we're going to have times e to the power of our rate, 0.045. And we're going to multiply that times the time, 3 years. And this will give us our ending amount. Oh, hang on a second. We do need to make a minor adjustment. It's dropping by this much. So we need a negative 0.045, because this would be without the negative that the population was growing by 4.5%. So we need to change that to a negative, or else we'll end up with a bigger value, which wouldn't make sense for this problem. Okay, so we're going to go 937 times, I can't see my numbers, e to the power of negative 0.045 times 3. So that's 818.672. All right, number 4. George bought a Boston whaler in 2004 for $12,500. The boat's value depreciates, which means goes down by 7% a year. How much is the boat worth in 2012? What will the boat be worth in 2020? All right, so our beginning value of the boat is $12,500 times e to the power of, it's going down by 7% per year, so I'm going to use negative 0.07 as my rate, and then we have our time after that. So there's my initial equation. Now, I need to answer 2 questions, 2012 and 2020. I need to figure out what is the difference in the amount of time. So from 2004 to 2012 is a difference of 8 years. So I'm going to do 12,500 e to the negative 0.07 times 8. And then to get to 2020 from 2004, that's a difference of 16 years. So y equals 12,500 e to the negative 0.07 times 16. All right, so those are the things that I'm going to have to key into my calculator. See if I can get this set up right. That looks good. So 12,500 times e to the power of negative 0.07 times 8. So the first answer is 7,140.11. And the second one, I'm going to press second enter, change the 8 to a 16. And that's going to be 4,078.50. All right, number 5. The original value of a painting is $1,400. The value increases by 9% each year. Write an exponential growth function to model this situation, then find the value of the painting in 25 years. So, the initial value is 1,400 times e to the power of, we need our rate, it's 9%, it's increasing by 9%, so that's going to be 0.09, and then times t. There's the exponential growth model that models the function, models the situation. Now, to find the value of the painting in 25 years, we're going to put 25 in place of the t in our equation, and then we can key this in to get the value of the painting. 1,400 times e to the power of 0.09 times 25. So that's going to be 13,282.83. That's a lot of money. Okay, number 6. The population of a town is decreasing at a rate of 1% per year. In 2000, there were 1,300 people. Write an exponential decay function to model the situation, then find the population in 2008. Okay, so y equals, the initial amount was 1,300 times e to the power of, it's decreasing at a rate of 1%, so my rate is negative 0.01, and then t for time. So there's my exponential decay function that models the situation. Now, to find the population in 2008, that's 8 years after 2000. So I'm going to substitute 8 in for the time. So this will be clear. See if I can get this right. 1,300 times e to the power of negative 0.01 times 8. All right, let's see what that comes out to. 1,200.051. Okay. You have some problems to practice on for homework, so I wish you all the best of luck with that. Please reach out to me if you have any questions. Hopefully this didn't feel too new to you since it heavily relates back to things you've learned before. I hope you have a great day, and bye for now.